Let us now do a strategic review of synchronous machines. So in many ways, synchronous machines are deceivingly simple. Okay, let me explain why. It is similar in some sense to circuit analysis section 5 of FE Electrical and Computer exam, where you just look at KCL, KVL, and you're like, how difficult can be this equation or understanding this theorem that the sum of voltage drops should be equal to sum of voltage gains. Sum of current entering in a node should be equal to sum of current leaving a node. Okay. If you want to convert a series voltage and a series resistor into a parallel current and a current source in parallel with the resistor, you simply have to divide the voltage source by the resistor and connect the resistor in parallel with the equivalent current source. All of those concepts are fairly simple and straightforward in isolation by themselves. Okay. The issue is that when you start connecting the dots and building upon multiple pieces of information, okay, multiple knowledge areas, that's where things become tricky. And that's exactly what happens, in my opinion, in synchronous machines. And that is the reason why I warm my students up by first going through induction machines and then diving into synchronous machines. Does it make sense, guys? Okay. So knowing that background and overview of synchronous machine, you need to recognize that things like power, torque, speed relationship for the most part are the same. And even the equations are the same, right? When it comes to synchronous machines and induction machines. Now, when we start talking about things like governor control for synchronous generator, this is a brand new concept. In fact, it might be a brand new concept for you up until the point that you started preparing for the PE power exam and you came across it for the first time. I wouldn't be surprised, right? Because typically at undergraduate level courses, you don't, unless you're taking machines too, right? You won't really get exposed to this. I got first time exposed to this concept in my graduate school. Okay. The idea is that when you increase the loading, okay, when the demand increases, the speed decreases. And speed is everything when it comes to synchronous machine. Speed directly impacts frequency, and frequency directly impacts what? Stability, right? In section number 4, when we discuss power system stability, when we discuss the torque angle, everything is dependent on the frequency. Why does the torque angle start running, right? What is that critical point by which we have to clear the fault? Otherwise, the kinetic energy buildup will be so much that you will not be able, that you will hit a point of no return, and the system is just going to spiral down into a complete chaos. Okay. So these are very abstract concepts, very advanced concepts. So you need to lay a very solid foundation. And we've attempted to do that by means of multiple lectures and discussions in the live training. Again, equivalent circuits, they are key to understanding the concept. So this is equivalent circuit. The equivalent circuit, again, for synchronous machine is deceivingly simple and straightforward. Why? Because a lot of students don't even care about this. What is this? Field circuit. Let me just focus on this because I have my equation that is given in the reference handbook that talks about the armature current, that talks about E naught E. Let me just focus on this, right? A lot of students are not even aware of, like, physically, practically, construction standpoint, configuration standpoint, what does the field circuit do? Where does it appear, right? Field circuit is super important. Can you give me just one reason why field circuit is important? Just one reason. I'm looking for a magic word. Guys, quickly. Excitation. That's why it's important. Excitation. Okay. And as you guys know, in the live class, in the on-demand, we worked out excitation of synchronous machines, synchronous motors, synchronous generators in so much detail using the phasor diagram that now we have a very good understanding of why a synchronous motor can act as a source of reactive power. Now imagine somebody completely ignoring the field circuit. They're just going about their business, working through the reference handbook, looking at the equations, plugging and checking, expecting numericals, right? With no clue about how do you excite a synchronous machine? What's the purpose of the field circuit, right? Why is it that when we have power loads with different power factors, different things happen, right? Why is the phasor diagram behaving in a certain way with one type of load and in a different way with the other type of load, right? So that's why I am telling you that synchronous machines is a deceivingly simple concept or a topic or a knowledge area. But in reality, it requires a lot of time and effort to prepare for. So keep an eye on all the content, live training content, the on demand content. If you have access to all of that and work through the problems using this perspective. Okay. Motor starting of synchronous machines, surprisingly, and it's kind of non intuitive, counterintuitive, right? That synchronous machines are not self starting, they need help, okay, to get going. All right. You know how you have SpaceX rockets? You know, you have the rocket, right? There are these boosters, correct? Has anyone seen a rocket launch in live? I once attempted in Florida. What's the place? Cape Carnival? That's in Florida, right? Um, uh, the name is slipping my mind. But SpaceX rocket launch was scheduled. This is years ago, right? But it was canceled because of the weather conditions and whatnot. Couldn't see it live, but I've seen a bunch of these on TV, like most of you, right? What is the purpose of these guys? And you can very visibly see when the rocket is launched, they actually are disconnected, right? Therefore, the initial thrust propulsion before the main, rocket gets engaged. That's basically the concept with the synchronous machines as well. You actually need to get them in motion. And there are multiple ways that we've discussed in the program, right? In control, and funny thing is that the motor starting, although it is not self-starting, the motor starting mechanisms that we use for synchronous machines are actually much easier to understand as compared to, I don't know what about you, but at least from my standpoint, even from an explanation standpoint, they're more easier to explain as compared to induction machines. An induction machine, by the way, is a self-starting. Induction motor is a self-starting. We discussed open circuit test, short circuit testing in detail in the program. Please go through that. Again, the importance of IF comes into play because that is the glue between the open circuit and the short circuit test, right? And then we have the synchronous machine theory. We have details around the power and the quadrature, axis, reactance, and so on. Okay, the torque equation, steady state, and the cylindrical configuration, salient pole configuration, and so on and so forth. Okay, so I hope you found this strategic review helpful. And even if you actually are watching this and now plan on studying for synchronous machines, or you have just wrapped up synchronous machines, right, and just looking at a summary, I think that these few moving points, moving pieces of the puzzle and a high level overview will help you spend the effort in the right direction. If you're new to this channel, please consider subscribing. On a weekly basis, I'm creating content for FE Electrical and PE Power exam preparation. I also discuss topics related to electrical engineering with a focus on power systems engineering. If you'd like to learn more about my FE Electrical and PE Power exam preparation programs, please visit my website, studyforfe.com.